Good morning. We're going to continue our discussion of the Earth's interior and the heat that we find in the Earth's interior. So if you take a look at this image, you'll see there's a timeline to the right. And down here at the bottom, it says 4.5 GA. So that's 4.5 billion years ago. That's when the Earth and the solar system were starting to form. Now the Earth formed from all the collisions of all this debris that made up the early solar system. As that debris ran into each other, made huge collisions, some of it sticking together, some of it not sticking together. It created a lot of friction, a lot of force and heat, and that heat got trapped within this growing planet as all this movement and friction was happening between all of these rocky bodies that were smashing into this early Earth. So a lot of heat friction. And you can see that early Earth was all molten. So no crust, no surface crust here. It was just a molten sea of lava all the way down to the core. Okay. As time went by and the solar system started to calm down, most of the material had been taken up by the sun or by the planets. Fewer collisions, which means you start to get a crust that forms. So time goes by and we start to get this early crust. Now it's still all molten in the interior of the Earth, and that heat starts to get trapped in there because now we have a crust that's covering up that molten interior of the Earth. So now we're retaining a lot of that heat left over from the early Earth, the early formation of the Earth. A lot of times we call it primordial heat. And we start to see a distinction in layers now in the Earth's interior. And if you remember, that all has to do with density. Material that is more dense, like iron and nickel, will go down, sink down to the center of the Earth, forming the core. Material that is less dense will move up towards the crust and towards the outer part of the Earth. So less dense towards the outside, more dense on the inside. But we still don't have all the layers. This is just the first part of the cooling. But more time goes by, and we're at the present, 4.5 billion years after the solar system started forming, and we get the Earth that we understand today, which is a solid rocky crust that's made up of all these different plates. Oceans and continents sit on top of that crust. But the heat inside of the Earth mainly is all the leftover heat from the early formation of the Earth. That primordial heat all has been trapped, and it's been slowly cooling over time, but not that fast. I mean, it's still extremely hot inside of the Earth's surface. We also get a little bit of heat from something called radioactive decay or radiogenesis. And that just means that near the crust and the upper mantle, so in this region, we have radioactive materials, things like uranium and plutonium, that are going through radioactive decay. And as they do that, they give off energy, which actually heats the crust of the Earth, heats that upper part of the Earth. So two sources of heat, primordial heat and radiogenic heat. Okay. Okay, let's take a look at another image. And in this image, it's showing another slice of the interior of the Earth. And it has it labeled over here to the side where it has the crust all the way down to the core. And it's showing you the different types of heat transport that you're going to see. So coming from the core, you have conduction. And you can see the arrows here are showing that you have conduction coming out from the interior. So one material releasing energy to another material. And then as you get into the outer core and into the mantle, you're starting to get convection. And convection is this hot material from the core, or at least that's been heated by the core, starts to rise. And as it rises up and gets further away from that source of heat, it'll cool down a little bit. As it cools down a little bit, it starts to sink. And we see that here, it starts to sink back down towards the original heat source. And even in the upper mantle, same thing. It rises, heats, and then sinks back down. So that's convection. And remember, the inner core is hot because of that primordial heat, that heat from the Earth's formation. When we get up to the crust or the surface up here, what we have again is conduction, where one material from the mantle or material from the mantle releases some of its heat into the crust, and that heats up the crust. And then that heat can go through the crust eventually and slowly be given off into space. All right, this image here, we just go through quickly. This is the image that shows us the radiogenic heat, and it has a timeline. So if you look down here at the bottom, we have 4.5 billion years ago. There were several different radioactive elements. That's what each of these lines are, the red line and the green line and the blue line. And it goes up to the top and it shows you heat flow. And all of these lines start higher 4.5 billion years ago. That means that's how much heat was released through this radioactive decay of these elements, which are over here in the early Earth system. Now, since they're going through decay and becoming more stable, the amount of heat that will be released from radiogenic heating or for this radioactive decay will decrease over time. And if you look at this line, as time goes by, it just gets smaller and smaller. That number showing how much heat is released gets less and less. And that's the same for all of them. Remember, this heat is mainly around the upper mantle and the crust. So these are elements that are going through decay near the crust or in the crust. All right, so the last image that we're going to go through today is this one of the surface of the Earth, and it's a little hard to see. But what this image is showing you is where is the heat coming from the interior of the Earth, and where is it seeping out of the crust? So where do we see the heat leaving the crust? What you see in red, there's quite a few spots here. Quite a few spots here in red. And what these correspond to on the Earth's surface are divergent plate boundaries. And the middle of the Atlantic is a big divergent plate boundary. So as the plates pull apart, there's a lot of heat that comes up because magma is coming up through that spot. And we see it all over the Earth. Now, places where there's the least amount of heat being released is these thicker parts of the crust. So these are areas where there's a continent with the land that we live on. That doesn't release as much heat because it has so much more crust to get through than those divergent boundaries here. That's where you're really getting a lot of the heat lost to the Earth's surface and then eventually to outer space.